All right, so what I'm going to be working through today is kind of a continuation of protein function. Like I said previously, we're going to be talking about protein function through the spectrum or through the I guess through the lens of um, hemoglobin binding to oxygen, myoglobin binding to oxygen, or any sort of protein binding to a ligand. Now, the dissociation, so the release of that protein ligand complex can be written ultimately as an equilibrium. So this should be somewhat similar to what you saw in Gen Chem 2 when you talked about equilibrium. If we have our reaction as PL, or the protein ligand complex, dissociating into the free protein and the free ligand, we can write that as Kd is equal to the concentration of the free protein times the concentration of the free ligand, divided by the concentration of the protein ligand complex. So the protein and the ligand will either be as one, the PL complex, or they will be separate from one another as free protein and free ligand, respectively. Now, in most conditions, in most scenarios, the ligand concentration is very large compared to the protein complex. Therefore, the formation of PL does not appreciably change the ligand concentration. So effectively what that means is there's going to be so much ligand in an environment that even if all of the protein was bound to the ligand, there's still a huge amount of that free ligand floating around in the solution. Now, the fractional percent of a ligand or of ligand binding sites occupied can be represented by this equation right here, theta. Theta is equal to the number of binding sites occupied divided by the total number of binding sites in the solution. Okay, so what that means is that there are going to be binding sites that are occupied as well as binding sites that are unoccupied. And that total number of binding sites that are unoccupied, the total number of binding sites in solution is equal to the total number of binding sites that are occupied plus the total number of binding sites that are unoccupied. And that's where we get this equation right here. Protein ligand complex concentration is equal or divided by the free protein plus the protein ligand complex, because the binding sites are either going to be open and accessible, in which case we look at the concentration of free protein, or they're going to be a part of the PL complex. So what we can do is we can look at that PL dissociation in this KD, or this dissociation constant, and we can rewrite this as PL is equal to free P times free L divided by KD. So all that we're doing there is taking this equation right here and rearranging it. We're multiplying each side by PL and then dividing each side by KD. And in some cases, that division is going to reduce it down to 1, and in others, it's going to leave our equation like this. So the protein ligand complex concentration is equal to the free protein concentration times the free ligand concentration divided by KD. Okay, so we can look at that equation, that theta, which is equal to, sorry about that. So what we can do is we can take this theta equation and substitute in this newly defined PL. So we've defined what PL is, and we can use that and substitute it in right here and right here, respectively. So what that will lead to is this equation right here. So this is a little bit of a jump, but we're just substituting in that PL, which is equal to protein ligand or protein concentration times ligand concentration divided by KD. Substituting that in ultimately is going to be simplified down to this right here, which theta is equal to, and there should be brackets here, free ligand concentration divided by Kd plus free ligand concentration. Now, this equation allows us to express the fractional percent ligand binding sites occupied as a function of our ligand concentration, because the ligand concentration is a little bit more easily monitored and dictated by um, the experimental design and setup. Now, visually, the equation represents a hyperbolic curve. So if we were to graph theta for a protein like myoglobin, what we would see is something like this, or something in just a moment. This is implementing, all that we're looking at here is, rather than using the terms protein and ligand and P and L, instead our PL complex is MbO2. That's myoglobin bound to O2. Our free protein, P, is Mb, and our free ligand is O2. So one of the things that's important before I show you the graph is looking at this right here. That PO2, that is because oxygen is going to be a gas. And so we can use, I believe it's Charles's law, to look at the quantity of gas instead of the concentration of a gas. So we're looking at the quantity by looking at the partial pressure of that gas. So Charles's law says that the quantity of gas absorbed by a liquid is proportional to the partial pressure of the gas above that liquid. We can easily monitor the partial pressure of O2, and therefore we can get something that's equivalent to the O2 concentration. So when we come up with this and we look at this equation and implement it, we're going to ultimately get something that gives us a percent saturation. So if we implement all of this with respect to myoglobin and O2 as the binding ligand, we get a Y or theta that looks like this. Now, Y is equivalent to theta. Theta is more general when we're talking about any protein or ligand. Y is when we're specifically talking about oxygen binding protein. But this is our hyperbolic curve. If you look at the y-axis, what this is showing us is that at the top, 1.00 is equivalent to 100% of the protein has bound to the ligand. And what you can see is, as that along our y-axis, you could look at this as 80%, 60%, 40%, 20%, and 0%. Well, our x-axis shows the rough concentration or the partial pressure of O2. Now, what this is showing us is that as our concentration or as our partial pressure of O2 increases, what happens to our oxygen binding sites? Well, they get saturated. They get filled up. And as we proceed along, looking at this following along the x-axis, what you see is that the percentage of those O2 binding sites, well, they're becoming more saturated. And one thing that I notice is that my percent binding sites that are occupied by O2, well, I'm at about 90% when my partial pressure of O2 is at 30. So when O2 binds to myoglobin, the binding curve or the binding increase is hyperbolic with the pressure increase. So this is not a linear relationship. A linear relationship would be if we double our oxygen concentration or double our partial pressure of O2, then we're doubling the binding sites that are occupied. This is a different than or this is not a linear relationship. This is a hyperbolic relationship. Now, 2 points on the binding curve are apparent. One of which is, and this is very important for any oxygen binding protein and any protein ligand complex, 2 points of the binding curve that are apparent and that are very important. This first one, I would argue, is maybe more important than that. That is the point of half saturation. Okay. Now, essentially what this is asking, or what I want you to take away from this, is what partial pressure of O2 gets your protein to be half saturated? Well, our protein is half saturated whenever our YO2 or our theta is 0.50 or 50%. Okay. So what concentration or what partial pressure of O2 would get us there? Well, 2.5 torr. Now, one thing that's worth noting is that we're determining this 50% saturation based on our curve. So if you can imagine that our O2 concentration increases beyond 30, maybe our protein would get to 91% saturated or 92% saturated. But that brings up the second important point, the point of full saturation. We never actually get there, but we get very close to it. We never actually get there. This is kind of like in a calculus class, the limit, it does not exist and everything like that. I was not a good calculus student, but I took 2 calculi. At any rate, we're not going to get to complete saturation. Not every single binding site is going to be occupied. And one of the reasons for that is think of the nature of an oxygen binding protein. What's the point? What is it trying to do? If you think about hemoglobin, it's trying to take oxygen that I inhale and distribute it to different parts of the body, different tissues. So it binds it and then releases it, which is the nature of protein ligand complexes protein ligand complexes and proteins that bind to ligands. They're going to bind them and then they're going to release them. So the first point, though, what is the partial pressure of O2 that gets you to 50% saturated? It's going to be 2.5 torr. Now, the affinity constant, also known as a P50, is when your KD is equal to your O2 pressure. So then your Y is equal to partial pressure of O2. If you remember the equation, and jump back, the equation at the top here, Y is equal to PO2 over KD plus PO2. Now let's jump ahead. When our KD is equal to our PO2, if you look at this equation down here, in the numerator, we've substituted out KD for PO2. So then if you look at each one of these PO2s as basically one PO2 and substitute in, that's where we arrive at this 1/2. So when Y is equal to 1/2, that's our P50. So when 50% of the binding sites are occupied, our pressure of O2 is equal to our KD. This KD is often called a P50. Now, oxygen pressure at which myoglobin is 50% saturated with O2, this gives us a little bit of information, or this gives us information about basically how strongly a protein will bind to a ligand, and in this case, how strongly myoglobin will bind to O2. A high P50 indicates a low affinity, and a low P50 indicates a high affinity. One of the ways that you could think about that, the way that I think about it is, do you need a lot of oxygen for that protein to be 50% saturated, or do you need a small amount of oxygen for that protein to be 50% saturated? Does it basically love O2 and in a very low concentration, it's going to grab all of it up? Or does it kind of not like O2 and therefore it will, bind some, but not all? Like it needs a lot to kind of be convinced. So whenever we're studying an oxygen binding protein, it's always very important to think about what that P50 is. Here's an oxygen binding curve, and here's how they can vary. I'm sorry about this showing up on a separate line, but here is a P50. I should probably change the color that I'm writing with, which I'm going to do right now to, let's go with yellow. Here's a P50. Okay, that shows up as green for this protein, this myoglobin protein, and then here's another myoglobin protein, which I'm going to label beta. Just 2 different myoglobin proteins. Well, between 2 of them, which one is going to reach 50% saturation with less O2? Well, that would be protein X. Protein B has a higher P50. It binds O2 with a lower affinity. So the lower P50 indicates high affinity, strongly binding. A low P50 indicates weaker binding. Now, this binding is considered weaker when it takes a greater oxygen pressure to reach half saturation. This is something that's kind of tough to wrap your mind around, but I think it's very important to consider that, think about these things as inverse. Low P50, high affinity for O2. High P50, low affinity for O2. Now, oxygen binding when you compare hemoglobin and myoglobin. Here what we have is a graph that shows our y-axis percent saturation with O2 and our x-axis is pressure of O2. Our black line corresponds to myoglobin, which gives us that nice hyperbolic curve, whereas our red line here shows the sigmoidal curve. Now, I don't want you to think or stress too much about these columns right here, the tissues or my stylus. I don't know where my stylus is. Oh, there it is. The tissues and the lungs. I don't want you to focus and get distracted by those. I want you to instead look at the shapes of these two different curves. Well, with hemoglobin has a different shape to it. It's a little bit more deliberate. The question of that is a good question of that is why? Well, the reason for that is because the makeup of these proteins is different. This is a big indicator that these proteins have different affinities and different kind of binding processes. Myoglobin, if you remember, is a monomer. Hemoglobin is a tetramer. It has 4 subunits. So it's a little bit easier for a population of myoglobin to become saturated with O2. Hemoglobin, it takes a little bit more. Hemoglobin has 4 binding sites per molecule. Hemoglobin must be able to bind oxygen in the lungs, and hemoglobin must be able to release oxygen in the capillaries. So hemoglobin wants to bind oxygen in the lungs where there's a lot of oxygen, but then release it whenever it gets to the tissues where the O2 concentration is fairly low. More than that, one of the things that you should take away from this is that the shape of that curve goes to show that the different subunits of hemoglobin are going to play with one another a little bit differently and play with O2 in the environment a little bit differently. Now, myoglobin has a lower P50. The oxygen binds to myoglobin tighter than it binds to hemoglobin. That right there is one of the 2 most important things that I want you to take away from this slide. First of all is just that right there. And the second component is the shape of these curves are influenced by the makeup of those proteins, a monomer versus a tetramer. Now, myoglobin is basically 90% saturated in the tissues, while hemoglobin is just 50% saturated. So if you think about hemoglobin in the lungs, what would you expect? It's probably going to be 100% saturated or very close to that. Whereas in the tissues, hemoglobin is going to be about 50% saturated. So what do you think that means? What I want you to think about that as, let's say that you shrank yourself down to a microscopic level and you grabbed a hemoglobin in the lungs, or a hemoglobin molecule in the lungs. It would have 4 oxygens, okay? Once it picks up those 4 oxygens, what's it do? It goes through the arteries, goes to the tissue, and then you go back to the tissue, or you go to the tissue, you shrink yourself down, and you grab a hemoglobin molecule. Now it's about 50% saturated. So it had 4 binding sites in the lungs, and all 4 of those were occupied. But in the tissues, now it's only got about 2 of those binding sites occupied. So what do you think that means? It went from having 4 to now having 2. Is that a good thing? Well, the way that I want you to think about that is in the lungs, it picks up the O2. And then in the tissues, it releases it. Does it release all of them or all of the oxygen? No, it doesn't. It releases basically 2 of them because the tissue O2 concentration is lower. Hemoglobin is going to release it, release 2 of those O2 molecules in the tissues. And that's exactly what we want. If we had hemoglobin in the tissues that was fully saturated and fully saturated in the lungs, That to me would sound like it doesn't actually deposit the O2 anywhere. It just kind of cycles from the lungs to the tissues and back to the lungs and the tissues. We want hemoglobin to release that O2. And where is it going to release it? In the tissues. Now, that's where I'm going to stop with this video. I'll pick up the next one and just or pick up a discussion of structure of hemoglobin in just a minute, where we're looking at that sigmoidal curve and the impact of it. All right, well, have a good one.